Apply Newton's method to the equation 1 over x minus a equals 0 to derive the reciprocal algorithm x sub n plus 1 equal to x sub n minus a x sub n squared, and then compute 1 over 1.6984 accurate up to 6 decimal places. Newton's method states that x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. In this case, f of x is 1 over x minus a, and f prime of x is negative 1 over x squared. We assume a is a constant, so the derivative of a is 0. The Newton method's formula is therefore x sub n minus f of x sub n is therefore 1 over x sub n minus a over f prime of x sub n is negative 1 over x sub n squared. We then simplify this expression x sub n minus 1 over x sub n minus a, this is the numerator, times the reciprocal of the denominator, negative x sub n squared over 1, or x sub n squared over negative 1. A negative times a negative is a positive, so we end up with x sub n plus x sub n squared times 1 over x sub n minus a. To simplify this expression, we find the common denominator. This is x sub n plus x sub n squared times the quantity. The common denominator inside the parentheses is x sub n, 1 minus a times x sub n. This is x sub n plus x sub n squared over x sub n. Cancel one factor of x sub n. We end up with x sub n times 1 minus a x sub n in the second term. This is x sub n plus x sub n minus a times x sub n squared, or 2x sub n minus a times x sub n squared. This is what we are asked to derive, and we did using the Newton's method. To compute 1 over 1.6984, we first start with an initial guess. The more accurate the guess is, the less step in the Newton methods that we would need to carry out. In this case, 1 over 1.6984 is probably a half, or 0.7 or 0.4. But let's say that we would simply use 1 or 2. Again, the further away from the actual solution, the more step we will need to use. Why not just start with x sub 0 equals 1? Again, it is better to start with x sub 0 equals 0.5 in this case. But this is okay. X sub 1 is therefore 2 times x sub 0 minus a times x sub 0. In this case, a is 1.6984. X sub 1 is therefore 2 times 1 minus 1.6984 times 1, and this will be 0.3016. We then use this and plug this into x sub 2. X sub 2 is 2x sub 1 minus a times x sub 1 squared. Plugged in x sub 1, which is now 0.3016. We have 2 times 0.3016 minus 1.6984 times x sub 1, which is 0.3016, and then square this. We will get x sub 2, which is approximately 0.448709, but we will use one more decimal place in the intermediate step. The question asked for 6 decimals, we will use 7. In the intermediate step, x sub 3 is 2 times x sub 2. X sub 2 is now 0.4487091 minus 1.6984 times x sub 2 is 0.4487091. Square this, we will get x sub 3 to be approximately 0.555462. But again, we keep one more decimal places. X sub 4 is 2 times x sub 3, which is now 0.5554625 minus 1.6984 times x sub 3 squared, 0.5554625 squared. We will use a calculator for this. We will get 0.586930. X sub 5 is 2 times x sub 4, which is now 0.586930 minus 1.6984 times 0.586930 squared. X sub 5 is approximately 0.588734. At each step, we want to round it to 6 decimal places to see if it's the same as the previous x. If it is not, we will need to keep going. X sub 6 is 2 times x sub 5, which is now 0.588734 minus 1.6984 times 0.588734 squared. And this is approximately 0.588794. And again, rounded to 6 decimal places, we see that this is 0.588789, which is not quite the same as the previous x. So we will need to do one more to see what happened. X sub 7 is 2 times x sub 6, 0.588794 minus 1.6984 times 0.588794 squared. And we see that this is 0.588789, which we round to 6 decimal places. We see that this is the same as the previous number, round to 6 decimal places, 0.588789. So we stop. We conclude that 1 over 1.6984 is approximately 0.588789. We use 7 steps to get to the answer. If we were to use 0.5, the number of steps will be reduced